Alright, welcome to the fourth video in this series. So today we're going to be going over some examples and a proof of the chain rule. And the chain rule is another way to take derivatives. But before we go into that, I want to emphasize something about the derivative. So, as we know, the derivative is like the slope of a function as the change in x approaches 0. So you get this instantaneous rate of change. I also want to point out that if you have your change in x, then your change in y, like your function, which is this squiggly line, the change of that function as delta x approaches 0 is also going to approach 0. If we take this same squiggly line and we have a smaller change in x, you'll see that this is a very small difference compared to that. And it makes sense because if you put those 2 points, like the distance delta x as it approaches 0, will have to be on top of each other. If it's not just with respect to x, it's also going to have no change in y, which makes sense. Like if you think about it as like time on the x-axis and your position on the y-axis, you can't change your position without a change in time. Like you can't just teleport from one place to another. So if you have no change in time, if time is on the x-axis, then you can't move. So your change in position will also be 0. And this will, this statement, as delta x approaches 0, so does delta y approach 0, that's going to be important for our proof of the chain rule, which we're about to go into right now. But first, what does the chain rule say? So if we have this function y, and inside this function y we have another function a of x, its derivative, the derivative of y with respect to x, is actually going to be equal to the derivative of y with respect to a, this part right here, times the derivative of a with respect to x. So we kind of just take the derivative of this main function right here, and then we multiply it by the derivative of this smaller function in here. It's going to make more sense as we do some examples. Well, we'll start with an example right now. Say we have ln of x squared. So we know that the derivative of ln of x just equals 1 over x. We proved that earlier. But this isn't just x inside. We also have x squared. So what it's saying is, okay, we find the derivative of this outside thing. We'll just ignore the inside, and we're going to multiply it by the derivative of the inside. So let's get rid of this real quick. So the derivative of ln of x is going to equal to, the derivative of ln is just going to be the inside under 1. So we have x squared. But we also need to take the derivative of the inside and multiply it. This would be our dA dx. And the derivative of x squared is just 2x. So we get 2x over x squared, which equals 2 over x. And that'll be our derivative of this function. I also want to emphasize that this is consistent with just ln of x, where you take the derivative of ln of x, which is just 1 over x, and then you also multiply it by the derivative of the inside. But the derivative of the inside is just x to the 1, and then we multiply it out in front, subtract 1, we get 1 times x to the 0, which just equals 1. So we just multiply it by 1, and we still get 1 to the x. We didn't go over that earlier because it's just repetitive. It's going to become intuitive that the derivative of x is just going to be 1 if you have it with respect to x. Let's go into the proof, but first let's make some room. So the derivative of dy dx is the limit as delta x approaches 0 of delta y over delta x. That's our fundamental definition of the derivative. Our change in y over change in x, our slope of a function, as the slope. And then if we take the limit of it as the change in x approaches 0, that's going to be our derivative. But let's move into our proof, where this is also saying that the limit as delta x approaches 0 also equals delta y over delta a times delta a over delta x. So where does this come from? If we look at this definition right here of our chain rule, dy dx equals dy dA times dA dx, well, the derivative is an instantaneous rate of change. So we can just substitute this delta symbol, this change, in y with respect to a times this change in a with respect to x. And we can distribute this limit function to that and multiply them. So this is the same thing as the limit of delta x approaches 0 of delta y with over delta a times the limit as delta x approaches 0 of delta a over delta x. We just distribute this limit function to each part of the inside. So notice how delta x approaches 0. There's no delta x in here. So we're going to come back to that in a little bit. But we see that, our derivative function, like dy dx, equals the limit as delta x approaches 0 of delta y over delta x. And that's pretty much what we have over here. We have delta x in the bottom, so as that approaches 0, we get dx. But we also, that's with respect to this function a, not y, a. A is this part inside. This would be in our ln of x squared example, a would be x squared, y would be ln of x. So we can just say that this is just dA dx. Now, we are saying that as dx approaches 0, we have this function a of x, and we have this small change in delta x. We're also going to have this small change in a. As we can see here, if you have no change in x, then you're not able to have a change in the y coordinate as it approaches 0. So what we can basically say is, say that's a. Delta x approaches 0, then so does delta a. So we can just rewrite this as dA approaches 0. So limit of delta a approaches 0 of delta y over delta a. Well, that's the same format as over here. So now we can just rewrite it as dy dA times dA dx. So that's pretty much the end of our proof. You'll notice that, let's just rewrite it, d dx of y of a of x equals dy dx. This function y with respect to x is going to equal the derivative of this big function with respect to a times the derivative of this small function inside with respect to x, which is what we have here. Dy dA times dA dx. And if we want to verify this real quick, we can see that the dA's just cancel and we're left with dy dx on each side, which kind of shows that it cancels out, so it's equal on both sides, so it's true. With that out of the way, let's just go through a couple examples. I think next video we're going to go over derivatives of sine, cosine, that stuff, and then we'll go into the product rule. But let's just go back to our simple ln of x. So we know that the derivative of this with respect to x is just equal to 1 over x, and then we take the derivative of this inside, which is just going to be 1, which equals 1 over x. You don't need to do that second part because we know the derivative of x with respect to x is just 1. But let's try again with a different function inside. Let's say it's 3x to the 9th. And if we want to find the derivative of this, then, well, we take the inside, 1 over the inside. That's just our definition of the derivative of ln of x, which we proved in, I think, our second video. But now we also need to take the derivative of the inside. So we do a little bit of power rule where we multiply the front by the exponent and then we subtract 1. So we get 3 times 9 times x to the 8th. So 3x to the 8th equals 1 over, 3x to the 8th over 3x to the 9th, which actually just cancels out and we still have 1 over x.